Our next talk is from Thomas Kluyver from the European XFEL. It's h5py, a bridge between HDF5 and Python. So Thomas, if you're ready, you can go ahead and share your screen and get started.
Okay, can you see my screen?
Yep, we can.
Super. So thank you. Yeah, I'm Thomas Kluyver. I work at European XFEL, and I'm also one of the maintainers of h5py since a year or two ago. And so that's the main capacity that I'm talking in today. h5py is one of two bindings for Python to HDF5. The other one is pytables, and really the difference in a nutshell is that h5py kind of tries to expose the HDF5 model as it is in sort of the most Pythonic way that we can come up with. And pytables kind of has its own model of how to store and work with data, and it uses HDF5 as a storage format for its own model. So if you're already used to HDF5, then h5py is possibly going to be sort of easier to translate to from other languages. And this will be a fairly sort of high-level general introduction to h5py. So I apologize if you've used h5py before. This will probably, a lot of this will be old hat to you, but hopefully there will be one or two bits that you didn't already know. So the context for how HDF5 and Python can really work together at all is the NumPy library. So this is a library that does multi-dimensional arrays, primarily numeric data in Python, and you can do operations like this that act on the whole array in one go. And this is really kind of the core of how scientific computing in a slow language like Python is possible, that you have one instruction like this that can be acting on here 30 numbers, but the same thing will work on 30 million numbers just as well, if you have the memory to support it, of course. And NumPy includes functionality for selecting part of the array easily. So this is slicing syntax. We're saying we want the first two things from the first dimension and the first four things from the second dimension. So we're taking out the top left corner of this array effectively, and this is quite flexible. If I want to say go from 2 to 6 and take every second one, and it can do that, for example. And arrays have a shape, so however many dimensions they are, and a d-type. So you can see there's kind of an obvious similarity here with the core features of HDF5. This is a lot like an HDF5 dataset in memory. And so h5py comes in. I'm using the release candidate of h5py3, which we're going to be releasing very soon. And in the simplest case, you can just assign a NumPy array into a file object like this. So I've created a file object, and by assigning to a name inside the file like this, I create a new data set. And if I h5 dump that, I'm using the exclamation mark here to run a shell command, you can see that I've got my 2D data space from my NumPy array has been replicated in HDF5. And going the other way to read that, so if you index the file object, you get a h5py dataset object. So this has just kind of read the metadata of the dataset from the file at the moment. And if you do a slice of the whole thing, this with just the colon means from the beginning to the end, then we can read all of the data, or like with slicing the NumPy array, we can read just part of the data. So this slicing syntax that's standard in Python is mapped to the HDF5 hyperslab selection. h5py, again, matching NumPy also includes, you can also index an array or a data set which drops a dimension. So this goes here from a 2D array or data set to a 1D array by just giving it a single number. We're taking the middle row of this data set. And like a NumPy array, it has a shape and a D type. So the HDF5 data space and data type have been converted to the equivalent NumPy representations. And there are other attributes that are available there, like n bytes, the number of bytes that it takes to store the whole of this data in memory. Of course, this just assigning an array into the file directly only works if that data set is small enough to fit in memory all in one go. So you can also call the create dataset method, and you can create an empty data set just from the shape and the required D type. And then we can produce some random data. So here we've got a sort of imaginary stack of images, 10,000 images, each 1024 by 1024 pixels, and we can fill the first image in that by doing the same kind of slicing and indexing that we did to read the data set. So this is reading and writing are very much sort of mirror operations. You can assign into a slice of a data set to write to it, and assigning from a slice of a data set reads from it. And you can slice it in different ways, and then the result is always a NumPy array, so you can immediately use NumPy methods on the data that you've read from that. So here we're taking the first 5 frames and then doing an average over both dimensions within each frame. So we can see that we've written the first frame and the remainder are empty for now. Create dataset also has options for various things, including defining chunks and compression options. So if we knew that data was highly compressible, we could say, okay, we want each image to be one chunk by itself, and do gzip level 1 compression on it, for example. And you can also, with a dataset object, you can inspect the chunks and the compression that were specified when it was created. And writing to it works just the same way, and then obviously HDF5 handles the compression internally. So the default layout, if you don't use any features that require chunks, is contiguous. But if you use compression or any of the other features that work with chunked data, you can either specify the chunk shape in this kind of format, or if you don't do that, h5py will try to guess a useful chunk shape for you, which is a fairly simple mechanism based on just kind of making the chunk within a sensible range of sizes. And I just want to give a shout out to the HDF5 plugin project, which is another Python package maintained by a separate group of people, which includes several important extra filters for HDF5, including, for example, the ZFP filter that Lee mentioned yesterday. So you can import HDF5 plugin and then use any of its filters in h5py. One of the particularly nice things to do with h5py is using it to create virtual data sets. This is an operation that is relatively lightweight and often not particularly time sensitive. This is something we're using it for at European Expo. So, for example, here I'm creating 4 files and putting a one-dimensional data set in each. We're going to our 1D data set here, 100 entries, and we're going to fill it with some data that counts up from the file number to 100 greater than that. And then we're going to make a 2D virtual layout. So this is a special object that h5py defines for kind of the process of making a virtual data set. So you define a 2D virtual layout here, and then for each of these source files, we're defining a virtual source, and we're mapping this source into the data set. And again, like reading and writing, this relies on Python slicing syntax. So for example, so here I'm saying that each position in the first dimension represents one of the 4 files. But for instance, if I wanted to say I only want to fill the first 50 entries in that 100 long dimension, and I want to take every second entry from the source file, then I can do that like this. So you map chunks of your source data into your virtual layout with this convenient multi-dimensional slicing syntax, and then you call create virtual data set, give it a name, give it a layout, give it a fill value for any empty chunks of that empty bits of that data set, and that's been created. And of course, reading a virtual data set is completely transparent. It looks just like any other data set. So we can slice that data set and read it into a NumPy array. So that all that I've talked about above is the high-level interface. So this is kind of trying to present the most Pythonic kind of interface to HDF5. So using sort of dictionary-style interfaces for files and groups, and NumPy array interfaces for data sets as far as possible. But h5py also has a low-level interface, which is kind of accessible from all of the high-level objects with this this .id attribute. So every high-level dataset group, a data type, file, object has this .id attribute to give you the corresponding low-level object. And here the methods are much more a one-to-one mapping to the HDF5 API. So this is calling h5d get num chunks, and this is h5d get chunk info. So there's pretty much always a clear correspondence between methods in the low-level h5py API and the methods in the HDF5 API. But it still makes all of the HDF5 calls kind of more or less Pythonic. So by that I mean things like default default parameters, or parameters where there is a sensible default, have a default in Python, so you don't have to pass them in. So for instance, both of these functions take a data space to indicate a selection in HDF5 API. The equivalent Python parameters have a default to say use the whole thing as a selection. And also, as you can see with this one, there's no like passing a pointer to fill in the data there. The Python wrapper at the low level still deals with allocating that bit of memory, passing that into the HDF5 function, and then converting the result into a sensible Python type. And it will also, if you do something wrong, it will also automatically convert the HDF5 error description into a Python exception, although our conversions there are not entirely reliable at the moment. So I mentioned that we're just about to release h5py 3.0. We've already made a release candidate, and hopefully the final version will be out very soon. So what's new? Actually, surprisingly, there's not that many sort of headline marquee features. We've dropped a few old bits of compatibility that were hanging around. We've done a few bits of work on performance, including releasing the GIL, which is the Python global interpreter lock, which means that only one thread can run Python code at a time. We now release that lock while reading or writing HDF5 data, so that something else can go and happen, for example, updating a GUI. There have been some reductions to the overhead for reading, particularly doing lots of small reads from the same data set can now be as much as 10 times faster. All of the string conversions between HDF5 and Python strings have been the rules for that have been redesigned. It's hard to kind of encapsulate that in one little example, but one visible bit is that there's this new asterisk wrapper, so that you can always read a data set to Python strings, regardless of whether that's fixed length or variable length in the data set in ASCII or UTF-8. And at our h5py code camp last year, that some of the HDF group developers joined us at, and John Reddy implemented this iter_chunks method. So if you've got a chunked data set, this will give you kind of the slices representing each chunk, so that you can read one chunk at a time through the high-level API like this. Although actually, another thing that's new in this version is exposing the low-level read and write chunk direct methods, which let you bypass the filter pipeline if you want to do that. So I think that's everything that I was going to cover. Are there any questions?
Did you see the one from Lucas in the chat window?
No, I didn't. I don't think I can see the chat window while I'm sharing my screen.
No problem. He says the virtual data set creates references to the other data sets that are on disk, right? i.e. there's no data duplication. And then Elena said, yes, data is stored in source data sets, very nice and easy BDS setup in Python. So.
Yeah, I think Elena has got that covered. Yes, Lucas, you're quite right. It doesn't duplicate the data.
Any other questions for Thomas?
Just admiration how easy things are done in Python comparing to C, HDF5 API, especially BDS. And strings, it's amazing. Thank you. It's really nice.
We did have someone ask if your notebook was available.
It's not yet, but I'm happy to. I think you were collecting slides
Yes.
for all of the presenters, weren't you, Laurie?
Yes. So yeah.
Yeah, I will send you this. And
Thomas, this is Suren here. This is very cool. I've always admired the h5py and how easy it makes for people to use HDF5. There have been a lot of talks yesterday about the walls, which we are developing a bunch of them too. How can h5py connect to walls?
as far as I understand it, because h5py is wrapping HDF5, then once you have HDF5 1.12 wrapped, which is also one of the things in h5py 3.0 that you can actually build it with HDF5 1.12. As far as I understand it, then it should just work. I think, fingers crossed. You should just need to set the right environment variables, and then HDF5 will use the vols internally.
Okay, so it's.
I haven't tried this yet, but
okay. All right.
I think that should be the case.
Okay. Thank you.
Alexander here. I want to just chime in. There is a now archived GitHub project, h5py vol, that actually someone created the ability to create a vol in Python and somehow connect it with the HDF5 library. Now that person archived it, so I'm not sure in what state it is, but that's an interesting idea that actually you could write a vol in Python.
Yeah, there's at least 2 of those I've seen.
Oh, there is more than that, Quincy?
Yeah, right. We did one at Berkeley and kind of paused it. I mean, it's still around. We could revive it. But there was another one at the
Barcelona Supercomputing Center.
Yes, that's what I was thinking. Yep. The data clay project.
Yeah.
Yeah, and I talked to a developer. He said it's yours now. So it's communities. So communities encouraged to contribute and support it. But he's available to answer questions. So if anyone interested, we'll be happy to connect you with the original developer. Paul Laura from, he's now at MongoDB, I believe.